Alrighty, class. I'll get started here. As you all know, we're going to be talking about topographic maps today. We've had an introduction last class talking about longitude, latitude, and some basic pointers, basic items that you find on topographic map and maps in general. But today we're going to specifically talk about the use of topographic maps. How do you interpret them? What are they? What do you use them for? But have you guys ever been on out someplace, the woods, camping, hunting? No roads, no compass, no map? How'd you find your way back? What do you wish you had?
A map?
A map. Has anybody here used a topographic map before? You have? Okay, good. Two? Okay, good. Three? Oh, very good. Well, topographic maps are used besides for hunters and fishermen trying to find their way to where they want to go without any roads available. But they're used by, I found out, they're actually used by interior design people. People who, they call themselves the interior design, not the kind of move furniture around. But they use them, the CAD programs, where they're designing things outdoors. Civil engineers use them. If you're going to build a tunnel, you better know how far you have to go, how wide the mountain is, and what height you're going to be drilling your tunnel. When you're building roads, you've got to make sure you take the right path. It's a lot easier going around the mountain than through it, so unless you intend to. Geologists, of course, environmental scientists use them. People in conservation use them, looking for swamps and preserves, that sort of thing, for birds and wildlife. So there's a lot of people that actually use topographic maps. So the normal everyday person probably doesn't get beyond the Google Maps. But today we're going to change that a little bit. We're going to go through the objectives. I have them written here too. Well, a little, you know what? We need change. Sorry about that. Okay, now our content objectives, we're going to understand the basic information found on all topo maps. We're going to read, read and interpret contour line patterns on a topo map. Trying to understand what the topo map is telling us. And then how these patterns reflect underlying geology. And then the language objectives, I have a handout that has vocabulary on it. We'll go, it's this vocabulary and some other vocabulary we'll be talking about. But our language objectives to understand some of the basic geologic and topographic related terminology that we commonly run into. But this is not for reading, this is for a guide, mainly for me. Pass these out. Pass those out. Now, the first part of this class will be pretty much the lecture. And as I go through, because in order to understand topographic maps, there's a basic terminology that we need to know so we can communicate. This form, as I go through and discuss what's on the screen, you're to fill in the blanks of these papers. This is important because this is the paper and other guides and other classes will be used for the final, for the quizzes. So it's important to keep track of these, fill it in, and know what's on it. What you fill in is what's on the test. So it's important to know that. But topographic maps, well, like I said, they're useful for understanding landforms, and the word topography pretty much just refers to the shape of the land surface. Those of you that have been out hunting and fishing and out outdoors camping realize that if you used them. But each topographic map is in, and I have examples of this too. But each topo, they come in quadrangles, and with these quadrangles, because it's a rectangle by 7.5 meters square, and they actually show the height above sea level. So the numbers, the contours, the lines you see on these things are going to reflect elevation above sea level. So in that reference plane, that sea level is the reference plane. It's important to know that because you need to have these numbers refer back to a datum. That datum, reference plane, is sea level. Topographic maps are three-dimensional representations. Well, actually, they're two-dimensional. You have a flat surface, contour lines on it. So you have a flat surface representing a three-dimensional reality. It's kind of like this. This table is our sea level. This is our topography. We've got a little hill out here. This hill is about, let's say it's 5 feet from here to here. Okay, you add another little segment to that. Yeah. There's another 5 feet. So there's your one contour. Let's say these are 5-foot contours. So there's sea level, 0, 5 feet, and then 10 feet, and here's the top of your hill, 15 feet. So that's essentially what you're doing. But each point here, each horizon represents a contour line. And it's like taking an invisible plane and just slicing that mountain at every 5-foot interval. And every time you slice that mountain, that's where a contour sits. And what a contour does, contour line, it will connect points, in this case of equal elevation. Now you can have a contour of, you have weathermen show contour maps all the time on the news. And those contours are connecting points of equal pressure or equal temperature. In this case, it's equal elevation, about 0. So a contour is just a line connecting points of anything. In this case, it's just elevation. So here's your 0, 5, 10, and we have an earthquake, straight line. So that's essentially the basic idea of a contour map. The thing is to be able to interpret all those different patterns of those various contours that are there. Okay. Now landforms, again, right here. It's just another physical data. Landforms, topography, pretty much the same thing. Now USGS has been, they've published these maps since the 1880s. And they're commercially available. I have a few I bought from USGS. And they're used, various sizes, various scales. But the main thing is that every map has basic information on it. You'll find the name of the map, the date when it was made or revised, reference data, which is important, the scale. Now you might hear it says in fractional or graphic format, so we'll see that in the maps I have. To measure, and also they're used for the measure distances on the map. And you have the contour lines, which are vertical distances, or the contour interval, which is the vertical distances between contour lines. Because you can have a line like this, that little mountain we built. The contour interval was 5 feet. Every 5 feet vertical height, you had a contour line. So that remains constant through the entire map. Where's map location? North arrow, magnetic declination. On these maps, or any map, north is always to the top. So if you get lost, you know which way is north. And then we have joining quadrangles. So if you want to find some other maps adjacent to you, you know what the order. But the single most important feature of these, single most important feature on a topographic map is the contour line. That's the most obvious thing it's on it. That's what distinguishes it from other types of maps. So, but important thing to note is one, they connect points of equal value. In this case, it's elevation. All right. The contour, and you'll come across this and use these points on the next slide as we look at these maps. They can never cross, because when you're looking through, you're looking through this, the 5-foot contour can't cross the 10-foot contour. So they just never cross. And the closer the distance between contours, the steeper the slope. Even though the map, the contours, the interval remains the same, the distance between the contours, if you have a cliff, here's contour 0, here's contour 10 feet, 100 feet, those lines are going to be on top of each other. Elevation. But if you get a slope, here's contour 0, here's contour 10, those contours are going to be further apart. You Even though that's 0, that's 5, it's 0, it's 5. These are on top of each other, those are separated. So the distance between contour lines reflects the slope. Steep slope, they're close together, that's the most extreme. Gentle slope, they're further apart. Okay, where are we? Okay, we did that. Any particular contour line can never branch or split. It's not like a tree. The contour line isn't 5 feet that way and then 5 feet that way in the same line. You have to have two different ones. So, and now you have a special type of contour represented by concentric circles, closed contour lines. We have a couple situations where you'll see on the map, you'll have contour here, contour here, contour here. Let's say this is 100, this is 200, this is 300. So the elevation is increasing from here to here. So you're getting something like that, right? So that's your mountain, hill, any raised elevation. But you can have, what do you do when you get a hole? Here's 100, here's 200, 300. That's represented by, and you have here, point 100, 100, 200, 200. You have it here, you have it on the other side. So there's 100, 200, 300. Same sort of pattern. The way to tell them apart is that they'll have hatch marks. So a hole. Now this hole, in geologic terms, is called a karst. You see in Florida, roads collapsing, sinking. That's another one. Very good. Out here near San Antonio, in Bonsfeld, we have caves. And that's how they start out. They start out with karsts. So, let's see. Karsts. And down here, when contours cross a stream, they form a V-shaped pattern upstream. So we'll know which way the stream is flowing. Here's your stream. Here's your stream. Your contour is going to come down here, and then it's going to go around. This is the stream. It's contour 10. Because the stream, the reason that is, anybody have an idea why that might be? Why they flow?
Is it going down?
Yeah, water flows downhill, right. So if the stream's going that way, it's not going to flow uphill. So this is getting 10, 20, 30, so this is much higher in elevation. So water doesn't flow uphill. Okay, but I have a little exercise for the page. The next page is going to be going through a particular map. That's why I had it. Now you want to pull the chairs around, make a little table.
Sorry.
This is the New Brunswick West Quadrangle. It's 7.5 minutes square. Okay. Now, what I want you to do is using these questions, using the questionnaires to go through, where I have put your name on the top and answer the question. It's next page. Next page. Now, we're not going to be able to go through this entire exercise, but we'll continue the next class and go through this so we can understand what's going on and the interpretation. There's a lot of details here. Now the scale of the map is at the bottom of the page in the center. It actually has several different scales associated with it. You'll have fractional scale, which is at 1 to 24,000. And then you have a graphic scale, which if you take a ruler to it, you can actually measure with your ruler how many feet it is. So at 1 to 24,000, that's 1 inch equals 24,000 inches, or 1 foot equals 24,000 feet, or 1 mile equals 24,000 miles. It's unitless. You put whatever units you want in there. But in our case, it's convenient. It's usually 1 inch equals 24,000 inches, which translates to 1 inch equals 2,000 feet. So that's the scale of this map. And if you measure with your ruler, underneath that graphic scale with an inch, that will turn out to be 2,000 feet. Okay, can you see where the contour interval is stated? At the bottom, underneath the scale? Okay, contour interval 10 feet. That's important to look at that because some maps are in meters. So, because I have another map, same area, well, this area and larger, it's in meters, put out by the U.S. Geological Survey as well.
This
So,
has all of the feet, miles, and.
well, that's the graphic. If you look at this contour interval, 10 feet.
10 feet, okay.
If you look at other maps, contour intervals are in meters. So you got to be really careful to look at that. So our class is coming pretty close to the end. We almost time to wrap up. We'll continue this with the next class, and as well as going through other geologic areas and other topographic maps to take a look at how the geology looks, how the topography looks with other types of geologic settings. But one thing I want you to note, if you take a look at this line, this green line, we have this vegetation. Green is the vegetation. It's a very sharp line throughout here. That also happens to mark a fault through here. If you take a look at the contour, if you were to drop this green, the vegetation helps delineate it quite nicely. But it's a very definitive fault line. Take a look at the topography across that line, perpendicular line. What do you see? Knowing that higher elevations have higher
They
numbers.
the lines are closer?
The lines are closer, so it's a very steep slope. What happens after you go further to the south? You go further to the south.
Contour lines spread out.
They spread out. What's in the middle? Can you see what's in that area? It's also outlined in green. Yeah, there's a creek, Connell Creek. It's a pretty big creek. But that creek follows that fault line. Okay. So, and also too, if you take a look at the feature up here, the northwest corner of the map, there's a small feature in the northwest corner of the map, right up through here, that has hatchet lines in it. Yeah, this here, the karst, sinkhole, right.
Oh, it's a sinkhole.
Yeah, you'll find these all over this area in New Braunfels, San Antonio area, because it's limestone. Rocks dissolving from the rainwater, forming these karsts, and eventually it'll form caves, so you find that a lot. Well, I'm going to have to wrap up, and time's coming to a close. We'll continue this exercise tomorrow, because there's a lot of details we haven't gone through. We'll finish the exercise and go through the creating a geographic profile across that slope of the river, so you see what the formation of that, what the geographic form of that river is relative to the slope. And also we'll get into looking at topographic maps in other geologic areas, say Enchanted Rock, it's granite, out in the volcanics, out in Big Bend Park, the recent faulting, you'll see fault lines in Houston. So take a look at all those and see how the underlying geology is reflected by the topography. And you never buy a house on a fault line. Bad idea, especially in Houston.
That's the ground grade is, what do we get?
So don't move to Houston and buy a fault and don't say I can tell you so. So yeah, California nasty place too. All right, any questions? Charlie, we got the heads by there. Okay, all right, well thank you very much. We'll meet again tomorrow.
Do you care?